Okay, hi students. In the previous video, we have seen the layout layouts of this two input NOR gate. So we have written so many masks, and then this is the micro wind drawing of that same two input NOR gate. So let us try to understand how does the 3D process of the same will look like. So you can just have a look at, okay, how does the 3D process will happen. That is, so let us start from the beginning. So now, okay, what I'll do is let me just start from the beginning now. So let me again start. Just have a look at how different layers are deposited. Now this is a simulation, so what we're going to further see is how does these layers are actually deposited on the wafer. So this is just a simulation using different masks. So now after this, let us actually go into the PPT and try to find out how does the thin films are formed. Now it is this is our VLSI process technology, and we are talking about the thin films. So the quality of the thin film has got many folds of its understanding. First is the composition. So we might have seen in the previous 3D view, so we were actually depositing N plus, P plus, metal, and then polysilicon, so and so. Of course, that is a very primitive or first level what representation of a CMOS implementation, but actually in the real sense, other than the materials that have been shown there, so we may have to deposit so many other different materials, so in which, so it may not be a single component that will be used, so it will be a combination of various metals will be used, or various chemicals will be used. So that's why composition of this titanium nitride TIN, so it depends on what is the percentage of titanium, what is the percentage of nitrate that you're going to add. So all those things matters whenever we are actually doing the deposition. And suppose if you are doing a metallization, so metallization need not be done using only aluminum, so we may have to have alloys of metals which can be aluminum and copper. So the composition of the thin film matters for the quality of that thin film. And then, okay, when we are depositing, so contamination also matters. So we have to see whether is there any unwanted metals that have been deposited, okay, during the process of deposition. Are there any water vapors that are there, okay, hiding, okay, they are being deposited over there, and is there any oxygen bubble or some gaseous bubbles are there trapped in the thin films. So these are the contamination. For a good quality thin film, there should not be any contamination. And once we deposit the thin film, it should be mechanically stable, and it should be stress, okay, there should not be any stress on the thin film. Suppose if there is any stress, or if it is not stable, then we cannot use the further processing on the same thin film, because when we are actually doing the fabrication of a IC, so there are so many layers have to be fabricated one over the other. Suppose if the bottom layer is not stable, then it becomes very difficult to have the subsequent depositions. And lastly, it has to have a very good adhesion to the bottom surface. It can be a substrate, or it can be some other material which has been already deposited before this thin film. So it has to, the material or the thin film should have a better adhesion to the the beneath material, whatever that has been deposited. And of course, coming to again thin film deposition, we cannot expect all the surface to be planar, so you may end up with a non-planar topography. In such case, So as you can see here, so in one case we have this is a non-planar topography, so in which even on the of course we have the top, of course the horizontal structure, and we also have a vertical surface. So if the deposition is perfectly of same thickness both on the horizontal as well as the vertical, so then it is the best we say it as that is the best type of deposition. We call it as it's a conformal coverage. So it is a conformal coverage if same thickness on vertical and horizontal side. But typically what happens is, so this is an ideal case, so typically what happens is something like this. So we will going to have thickness on the horizontal will be far greater compared to the this vertical thing. So vertical will be okay. So this is on the side it will be so less. You can see this is the side one here, so the side one is very less, and but on the horizontal side it will be more. So what is step coverage? It is the thickness of horizontal side thickness to the deposited on the okay. Let me just okay, this is okay, horizontal, this is the side, this is side, and this is on the top. So this is your side here, this can you see, this is on the side and this is on the top. So thickness on, so this should be vertical side. So let me write it as this is okay, vertical side thickness to the top side. Yes, okay, this is fine now. And this is typically what happens. So this type of step coverage results in high resistance, and mechanical cracking will also happen. Finally it will end up with a failure of the entire deposition. Suppose it is not properly deposited, then we think that okay, this is connected to this, but because of this poor step coverage, so you may end up with a non proper coverage of the thin film you're going to fail. So these are the thin film filling issues. So here you can see this is a space between the oxide where you are supposed to fill the metal. So this is a perfect filling where we are filling this gap perfectly with the metal. Suppose if you are filling some oxide between the two metal layers, you can see there is a air bubble left out, which is a void over here in this region. So these type of what voids will create reliability issues, which is not an acceptable thing during the thin film deposition. So these type of fillings will create issues in the working of the circuits. And if you can see here, this is the bottom coverage. So we expect this bottom should be filled with the metal because of this higher aspect ratio, where we have the width very small compared to the height. Because of this higher aspect ratio, so there is a poor bottom coverage. So this bottom is not at all covered here, the full length is not covered. So these type of problems are there whenever we are having a higher aspect ratio. So we have to ensure that the aspect ratio should be not too high, that will end up with this type of bottom filling not happening properly. So bottom coverage will be an issue if the aspect ratio is more. So these are some of the examples, real-time examples of poor step coverage and voids between the whenever you're filling something between metal layers. So we have this okay, air gaps that are being get filled out, so that have been created. Of course here, of course, so it is here we have a titanium, tungsten, and then aluminum and titanium tungsten. So these are the layers that have been deposited, but over here it's a very poor step coverage. So on the horizontal side we have a good thickness, but on the vertical side it is so poor thickness. So this ends up in what failure of this entire deposition. Let us move on to thin film depositions. So we saw what is the quality of the thin film and all those stuff. Now let us look into the vapor deposition techniques. So what is this thin film deposition is? So of course one of the possibility is vapor deposition. So in this vapor deposition, the constituents of the film are deposited or delivered through gas phase to the surface of the substrate to form the thin film. So assume that you are having a metal, it can be aluminum. So constituents of the film, in this case it's aluminum, will be delivered through gas phase on the surface of the substrate to form the thin film. So sorry, it's a what gaseous form of that aluminum will be just blown over the substrate so that it settles down on the substrate to form the thin film. So one of the way of doing this vapor deposition is chemical vapor deposition. So in this chemical vapor deposition, chemical reaction of the reactant gases with the substrate surface will form a thin film. So there is a chemical reaction happening between reactant gases which contain the material to be deposited. It will react with the substrate surface and we're going to have the thin film formed over the substrate. So usually, so we're going to have a silicon or dielectric deposition will be done using this CVD process, and it is going to have a good quality thin film. It results in a very good quality thin film. So this is one of the advantage of this CVD process, and it has got a very good step coverage. So both horizontal and vertical deposition will be almost equal. So that's why it is a good step coverage, and of course the conformal deposition will also be there. This is how a chemical vapor deposition will happen. One of the technique is this is also called as atmospheric pressure CVD. So the pressure at which this will be operating is the normal atmospheric pressure. If you can see here, so here this is a process where they are trying to deposit the silicon on this surface. So now this is the what a constituent which is in the form of liquid, so that will be bubbled through this the hydrogen is bubbled through this liquid, and it will be carried onto this chamber where we have put these silicon surfaces. So we may have to sometimes deposit even silicon on this one on the silicon surface in some cases where you want to have a very good silicon of the desired property and all those stuff. So you can see, so we have so many other gases which will going to carry these constituent material that is there coming in the form of gas. So we have a quartz reaction chamber, and this is called as cold wall system. So here this wall of this particular chamber is relatively kept cool, and the substrate and this graphite susceptor where it holds the wafer are only get heated using this RF induction, so which is a heating coil. So it actually heats up only this wafer and the graphite susceptor. So what will happen is, when it is get heated up, only the susceptors and wafers are heated. The wall is kept cool to avoid the deposition on the walls. Suppose if this is also hot, the deposition will also happen on the surface. To avoid that, this will be kept cool. So what is that is deposited usually using this type of cold wall system is, so it will be epitaxial silicon, or you can have a silicon dioxide will also be deposited. It can be doped or undoped. Okay, whatever doping concentration you want to have, that will also be passed through these gases what is that is available here. So using these gaseous form, you can able to deposit the desired thin film on this silicon wafer. So this will be operating at the atmospheric pressure, and you can see it's not very hot as in the case of your oxidation, where you will be heating it into an order of 1800 or 1600 degrees centigrade. and this is what is APCVD process that will happen, meaning okay, atmospheric pressure chemical vapor deposition. It has got different phases. So in the first phase, whatever transport of reactant by forced convection to the deposition region. So meaning, so we have, this is the deposition region. So to this region I need to bring these constituent elements onto this. So that is the first process. The first process is you should bring these constituent material to be deposited onto the wafer, have to be first brought in. So that's what is this. So that's what is the first process, where transport of reactants by forced convection to the deposition region. So there will be a gas stream which will be helping them to come over here. Then second process is transport of reactant by diffusion from main gas stream through boundary layer of the, okay, now you have a boundary layer. So this is the entire case region where the deposition will happen, in which we have a boundary where of course this gas stream is running at a higher velocity. So at the bottom it is not that much higher. So this is the boundary area where we're going to have the deposition to happen. So some of the constituent material is going to drop down here. You can see the transport of reactant by diffusion from the main gas stream through the boundary layer to the wafer surface. Now we're just actually dropping it out. Next is adsorption of reactants on the wafer. Now they are sticking onto the wafer surface. Then surface processes including chemical decomposition or reaction, surface migration to the attachment sites such as atomic level. Okay, now what will happen is these are all very small in dimension. They'll be just settling on the wafer. They'll be settling on the wafer, and this will end up with deposition of whatever that material you want to deposit. Now it will be get deposited over here on the wafer. Then once they got deposited, so now you can see you have lots of material being deposited. Next is dispersion of byproduct from the surface. So once you are left out with some byproducts, they have to be taken out. They have to be taken out from the surface, because this gas stream is keep running at a certain velocity. They are going to take out the unwanted material byproducts. Transport of byproducts by diffusion through boundary layer back to the main gas stream. So you have a main gas stream which is keep flowing there. So this will be taken out, and there'll be at 7 transport of byproduct by forced convection away from the deposition region. So they'll be taken out from the deposition region. So if we just go back and see here, so this is your material to be deposited. They will be bought here, and they're going to have interaction with the wafer, and if there are any byproducts that are coming, so that will be coming and then finally going out of this entire structure through this vent. So that is what is everything will happen at atmospheric pressure. So that's why it is called as APCVD. So APCVD, atmospheric pressure CVD. So next is so that is one atmospheric pressure. So next there are some possibilities where you can now you can see there in the previous process APCVD we just put a few number of wafers horizontally placed. Suppose if you want to do deposition of too many number of surface on the wafers, they can be stacked like this. The wafers can be stacked like this. The pressure can be reduced to a lower pressure, and one thing is that there is a slight heating will happen. There is a furnace which will be get heated. You can see there is a furnace with resistance heaters. So there is a stand for wafers. All the wafers will be placed like they are lined up, and since it is low pressure, so there is a vacuum pump that will be used to take out the pressure before we start this injection of the material onto this chamber. So first a vacuum pump will going to take out the pressure to make a low pressure CVD process beginning. So once everything is set, once the pressure is set for the desired level, then these source gases will be released on a control basis, and they'll be get deposited on these stacked wafers. This is an example of, okay, of course, not to worry about the equations what we have. So I just want to show you what is the typical rate at which, okay, all these things will happen, because you can see there is a pressure available, there's a total pressure, and there is a pressure of the incoming species. So these are all different pressures what we are talking about, and there is a gas concentration also will matter for the rate of deposition. So considering all these parameters, not only the, of course, it just refers to the pressure that is there in the chamber, and what is the gas concentration, what is the density of the film. All those things will matter for knowing what is the amount of deposition that is happening per minute. You can see with these specifications, so it will going to have 0.14 micrometer per minute. So for every minute, so there is 0.14 micrometer of a particular material be deposited on the given surface. This is how the thing will happen. So this is again representation of how does the deposition happens. This is a silicon deposition. If you can see here, we have so many different sources which is having silicon as one of their, okay, constituent. So either you can use this SiH4, this is with nitrogen base, this is just SiH4, you got SiH2, Cl2. So we got different types of gases which can be used for depositing silicon on the wafer using CVD. And you can see the growth rate is also given in logarithmic scale, and you can see the temperature is also given. So now in this case, if the temperature, of course it is inversely proportional to temperature. Suppose if temperature is more, then the growth rate is better. That is, the deposition of thin film on the wafer will be better and better if the temperature is more. So of course it also depends on what type of, okay, a source that you have here. And of course this almost becomes flat, so if you are having very high temperatures, this is not like a linear one, so it almost saturates beyond a temperature of maybe around 1000 degrees centigrade. This is again, this is at atmospheric pressure, and this is at very low pressure. Okay, how does the deposition will going to change? So this is because we had two types of deposition. One is low pressure deposition and the atmospheric pressure. So this is, of course, Hg is one of the term which is used in our one of the equation here. So this is Hg. So all those things will matter for trying to understand, okay, that will actually decide what is the growth velocity on the substrate. And we have this, okay, after going through that atmospheric pressure CVD and then low pressure CVD, then comes the plasma enhanced CVD. So in this plasma enhanced CVD, so as the name itself indicates, there is a plasma that is enhancing the CVD process. First thing is that why is this type of CVD required when we already have this, okay, atmospheric and low pressure, and when it is used? So usually we know that the depositions will happen, okay, there are n number of depositions have to happen. Assume that we have already deposited one material and we want to deposit another material which actually requires larger temperature. So in assume that, okay, you have aluminum deposited, and after deposition of aluminum, suppose if you want to deposit silicon or silicon dioxide, so you cannot put that wafer onto the furnace, because if you put into furnace, the temperature goes to maybe around 1800 degrees centigrade. When the wafer with the aluminum deposited if it is elevated to a temperature of 1800 degrees centigrade, we know that the entire aluminum which is deposited will be get it will be get because its boiling temperature is around 660 degrees centigrade. So that will be get okay. The deposition of your aluminum will be lost okay because of that high temperature. In such cases, we may need to have the deposition after aluminum deposition. If you want to deposit silicon, you cannot go to oxidation chamber. You have to come to these type of CVDs where we can able to achieve the deposition of same silicon, a good quality silicon at a lower temperature. So how it is possible with lower temperature is, of course, we can certainly do with this okay using APCVD and LPCVD, but the thing is that it actually takes longer time at lower temperature to achieve that. So that's what we saw here. Suppose if we just go here, so if you are operating at a temperature of around 400 degrees centigrade or so and so, then it takes a very long time for it to, because you can see the growth rate is very less. Suppose if you want to deposit 1 micrometer, so then it takes huge time at a lower temperature. So in such case, these normal CVDs are not okay, not useful. So we may have to go for plasma enhanced CVD. So how it is achieved is, along with a lesser temperature what you have, so there is a plasma used to speed up the process of deposition. So along with thermal source, you have a plasma source that will be used to make the deposition to happen a bit faster. So now this plasma is nothing but a highly ionized gases. So even, of course, there are possibilities that even at room temperature you can able to use this PECVD. We call it as PECVD. So this is how a PECVD chamber will look like. So you can see there is a RF power that will going to make the formation of this okay, plasma. If you can see here in this, in plasma enhanced deposition, the energetic species are used to help form the films on top of the wafer. So this is a wafer. So we want to use the energetic species are used to. Now the wafers are placed on the lower plate electrode. Heat can be supplied to the wafer through a heater beneath the electrode. So there is a heater which is going to provide the heat to this. A glow discharge or a plasma is sustained between the lower and the upper electrodes. So you can see there is a plasma that is being created. So this is created by applying a high electric field at a frequency of 13.56 megahertz at a lower pressure between 50 millitorr to 5 torr, creating ions and free electrons. Okay, this is the okay what plasma what we are talking about. This plasma will going to have high energy electrons which will strike the okay, gaseous which will going to contain those particular okay, material. So it will be depositing on this wafer which is placed at the bottom. So these wafers are heated by this heater, and there is a RF field that is applied which will make a plasma. These plasma will assist. You can see we have a gas inlet which is coming over here, so they'll be get coming over here. So once they come here, so these energized electrons will go into okay decompose these okay silicon, and then going to deposit on these wafers which are there placed beneath. So this will happen at relatively lower temperature and at normal pressure. So pressure need not be very low also. So we will talk about this physical vapor deposition in the next video. So this is what is the CVD process all about.